A little bit more conventional. I typically would like to write in real time, but since we can make like previous class, I'm going to write down the root of the theorem that I was trying to tell you about before the Thanksgiving break. And then if we need stuff, I can fill in more details, like, on the notes, just to make sure. But I'll go slowly, kind of like explaining the main ideas, but it's like, oh, man, I might as well write it down, just to kind of like make it a more streamlined presentation. Is that I usually don't like that because I feel that you go too fast, right? And then like no one has time to kind of like process it, so I'll try to go slowly, um, just to show you what we're supposed to do. But the idea again, like what I was trying to explain to you was kind of like if you have you have to go back to the top three problem, which is you were trying to find the mean of a function, right? Or like you just imagine that the function depends on n variables, right? This is like a usual problem without constraints. The mean will be a critical point or the gradient value, right? But if there are constraints, then you have to be more careful. So you are used to the Lagrange multiplier problem constraints, right? Where the constraints are quantities, but it's also important to understand that inequality case, right? So in the non-negative matrix factorization case, you want all the variables or the entries of the matrices to be non-negative. Right? So kind of like the analog of that would be that each variable has to be greater or equal to zero. Okay, so you're trying to find the mean of the function subject to the constraint that each variable is negative. But it doesn't take that much effort to kind of do it in a slightly more general situation where like the more general situation is like the one that you see here, where you're trying to minimize a function and the constraints that the variable x satisfies is like some sort of like linear inequality. So like that's kind of how we were doing it before the break, if you remember. So you have some matrix for silly reasons, the way I define things, like I'm actually using the transpose of that matrix, but you have some matrix that and then so you're asking that the matrix times the vector of variables is that equal to another vector. Okay, and that kind of like has as a special case that is non-negative case is a special case of that inequality. And this is kind of like similar to the type of problems you do in linear programming if you take that class. The only difference there is that if you take linear programming or linear optimization, that's another name for it, the function f will be a linear function. So it's going to be like a dot product of like the vector x to some other. So I'm doing it in more generality. Actually, you don't have to assume that f satisfies any particular conditions except the fact that you get the derivative and all that. So it doesn't even have to be convex or anything as I'm studying it right now. Ooh. And then there's like these KKT conditions, which are like named after Larouche, Jules, and Tucker, which says that if you happen to have a local mean of this problem, like a point that is a local mean for this function satisfying these constraints, then you can find some non-negative values. Okay. Some non-negative numbers, lambda one up to lambda n. Here n, what's the number of like, the number of like rows of like the matrix. So it's the number of inequalities that the vector has to satisfy. So you can find these non-negative numbers that make this equation called. So the gradient plus the sum of the lambdas times the vector AI gives you the vector. Okay. So in the non-constraint case, if there were no constraints, like you don't see this term, and that's just saying that the gradient at the time what happens at a critical. If you have a mean, you don't create that one, and then that's on the unconstrained case. So this is now what would happen in the more general case. These lambdas are the Lagrange multipliers, so that's why I'm writing it as the lambda, so then you think of them as Lagrange multipliers. In linear optimization, they're called like the dual variable. So there's like when you have a linear program, you can find the dual, like again, if you take that file, these two you have variable results. And in fact, there is this condition that the lambdas, in addition to being non-negative, have to satisfy this condition, which is called slackness. So like complementary slackness because one of the one of these lambdas times AI x minus bi has to be zero. So it's not like it's a vanishing condition. Either the lambda is zero or this quantity is zero.
So like, where is it? All of those.
No, I'm about to prove it, or
Oh.
I mean,
Yeah.
yeah. No, I was about to prove it. It's just that I thought if I write it down as I usually do, we can play it forever. And since we had lost that class, I can just wanted it to kind of be more like ready to go kind of thing.
Yeah.
Yeah. I'll show you right on.
Practice on the front on the class, which is in quality.
Yeah.
It's after gradient.
Equals land right, like equals to the grade the like lambda times the grade of t, right?
Right. Wait, so how does the lambda I minus? How does the subsequent, like, where does that subsequent?
Oh no, I'm about to you'll see it. Like I'm about to show you what.
This is the inequality generalization.
Right, let me say inequality versions. Yeah. It's the inequality version. In fact, if you look at the problems that I added, I put like one or two problems where you have to use that KKT condition to find the mean. Like a fun problem. It's not super complex. I mean, I didn't put anything crazy, but it's good for you to get your hands dirty to see how KKT is like really important, so. It applies in many different circumstances. I mean, there are more complicated versions. I'm just doing the one with linear inequalities because of what we put.
Or the equality case, you say that the equality, like the special case of the equality.
Yeah, because
Have like two inequalities.
correct, right, and equality is two inequalities. Yeah. That's you can only do the trick. Yeah. So that's why you can set it up as an inequality, and if you have an inequality, then you're saying that, yeah. If x is less or equal to equals 3, that's a way of saying that x is less or equal to 3 and minus 3 is, so yeah, like in the inequality case is more general in a sense. That's kind of how we should think about it. No, the proof is really cute. And it uses this Farkas method that I had mentioned last time, so that's why also it works. Because convexity is like a very powerful idea. So it doesn't just give you kind of the taste of how convexity is supposed to work. And then on Tuesday, I'll tell you the other piece of how convexity is also used for this type of problems. A different type of problem with this matrix completion. Thing. Well, that's what I was saying. Here, like, I'm not really asking for the function to be convex. But if the function happens to be convex, one of the reasons why convex functions are nice is because a local mean is automatically a global mean. So that's why, like, if you can guarantee that your problem is a convex function, or like, that's a useful thing to know ahead of time. Then doesn't need like you get an absolute minimum. Okay, so let's see. Okay. Like I was going to show you that in a moment, but I might have already here. You mean like in this case, like this case, you mean like this one, or just I mean just like if if you had like three inequalities, right?
Like, is it known, like, you pick a B and then?
Well, I mean, you have to. Why is this moving by itself? Is this obsessed? What I thought it was my own president. Okay. Maybe we're being whatever. Let's see, enough. That's kind of funny actually. For the record, I think they like like a projector and everything, like I feel like in a different circumstance, if you have like inequality constraints, like the p's are just like the constant coefficients because they're linear constraints. But I mean, yeah. So I mean, it just depends on which inequalities you're working, right?
So like, well, we know, like, we would know B before. It's not.
Oh, right. Like, well, in the setup, in the setup, right, like you have knowledge of the matrix A and the vector B.
Okay.
Yeah. What I was going to say, is that what does it mean, right? What does it mean that that the place where the mean happens must also satisfy the inequalities, right? So it's a point in the convex set. I did forget to say that, right? Which I had mentioned last time. The point of like having one of the reasons why this is like a nice problem to work with is because linear the points that satisfy a linear inequality, it looks convex, so like it's like a convex set. You remember a convex set, you pick 2 points on the set, the line segment is completely inside the set. So that they're like that's kind of what makes this like work nice. Okay, so if you have the vector where the function is has a local mean, right? This point is in the convex set, so it must satisfy, it satisfies the inequalities of the convex set. Okay, which in practice again, like what does it mean? Like if you do the multiplication of the matrix times the vector, it's a bunch of dot products, right? Like a matrix multiplication with the vector is a bunch of dot products. So it just means that all these dot products must be less or equal to the entries of this vector B, right? So
All those are non-negative.
well, no, like here, like the non-negativity is not being used. Like it's more like what is the interpretation of like a matrix times a vector? Yeah. Correct. Uh, but now because these are less or equal to, right? There would be maybe certain, this is a system of inequalities. Maybe there's some of those inequalities that are actually achieved, meaning that for certain of those inequalities, you do have like an equality. So that's what the activation set means. It's just like those indices, right? For which of the system of inequalities does the mean actually achieve the upper bound, right? So it's for which indices AI dot the X mean is BI. So it's kind of like that, it's kind of like where the inequality becomes activated. So if you want to do like a picture, maybe let me draw the picture here. Like for example, the convex set could be this triangle that is defined by linear inequalities if you write it down. And so if the minimum happen along this hypotenuse, right? Oops. Uh, if this is where the mean occurs, if the local mean happens here, that means that the local mean is satisfying the equation that defines the hypotenuse, right? Like, so the equation of the hypotenuse is kind of like being turned on, like activated at that mean. So at the mean, at x mean, let's say like if let's say this, this inequality could have been like x plus y less or equal to 1, right? And so at the mean, like x plus y equals 1. So like that inequality would be turned on, like activated, let's say. But like the other two, the other two inequalities that define this convex set is that each of the variables is non-negative, right? And so, if you thought about the convex set as being defined by, x plus y is less or equal to 1, and 0 less or equal to x, and 0 is less or equal to y. At this point on the mean, at this point mean, x mean, neither of these two are being activated because neither of the two coordinates is here. So only the first inequality being activated. Right. It's good observation, right? Like if the mean have happened to be here at this corner, then the hypotenuse equation is activated and the x equals 0 is being activated as well. So that's kind of like what the base is, right? Like the extreme points of a convex set are like, where these intersections compared, right? It's possible to activate them. Well, I mean, it's like that, in this case, in the geometry, right, you cannot, I mean, unless there's kind of like some redundancies, right? Like, not like, list from these ones, right, like, yeah. But, I mean, yeah, if we have, it's kind of like the same, if we have certain inequalities that are linear combinations of others, so they could accidentally be activated once the others are activated, right? But not like they're kind of like independent in some sense, So all that I'm saying is that the activation set just keeps track of those inequalities that are actually achieved at the mean. If that makes sense. And then you kind of like okay, so for those that are achieved at the mean, those inequalities that are achieved at the mean, you kind of like make a matrix, a smaller matrix whose columns just consist of these vectors where everything is like activated. Okay. And like here's like a very interesting interpretation of what the KKT condition says. So again, I want to show that this happens, right? Showing that this happens if you move the gradient to the other side, right? No, if you move the gradient to the other side. You get this, right? But this is kind of like expressing the gradient as a linear combination of vectors where each of the coefficients is non-negative. That's essentially what the cone of a matrix wants, right? That's what we talked about. That's why I talked to you about last time about the cone. So as a picture, what I'm trying, my goal is to show that the minus the gradient vector is in the cone of the matrix generated by this activation. Because almost by definition of what it means to be in the cone is precisely that it is a linear computation with non-negative quantity. Okay. How do we do? Okay. How do we show this? And this is where the Farkas lemma is kind of like a fun thing because okay, to show like what Farkas lemma said, maybe I should go back to that for a moment, is that there are only two possibilities, which kind of like if you draw the picture, it looks very clear, but it's kind of like, yeah, this is what Farkas lemma said. There are only two options. Either a vector is in the cone of the matrix or like the cone of some vectors, or the vectors can be separated from the cone. So it's one of these separation lemmas, which again happens for convex sets and where convex sets are used. So being separated means that you can find a line, what looks like a line in this case, but it would be a hyperplane in general. You can find a hyperplane where the vector is on one side of the hyperplane and the cone is entirely on the other side of a hyperplane. So Farkas lemma, and even I think in computer science and or combinatorics, there's like a Farkas branch that it was kind of important. Kind of how there's this doing of works for computer science, which is kind of the novel version of because they don't computers with like double design like that double press. But there's kind of like a Farkas practice also. But so it's kind of like it's like actually like a very useful result. So what Farkas lemma says is that either you're in the cone, or if you're not in the cone, you can be separated from the cone by a hyper. And only one of those two things can happen. So what I'm going to show, okay, so just to go back to what I want to do. since I want to show that minus the gradient belongs to the cone, right? What I'm going to show is that the other option is impossible. So I'm going to show that it is that this picture actually does not happen. That the minus the gradient cannot be separated from the cone. If I know that that's impossible, then that forces the other one, the other alternative to work. Okay. And then, what is a nice way, right, to prove that something is impossible? By contradiction, you assume that that actually happens. Right, so now by contradiction, let's pretend that we're actually in this scenario where the minus of gradient can be separated from the cone, okay? Okay, but again, what does that mean at a practical level? If if this were to happen, then you can find this plane that separates it, and this plane is specified. Any hyperplane can be specified by a normal vector, right? It's not like compound equation. The normal vector of the plane. There's kind of like a generalization for that for hyperplanes. So that means that you can find a vector y that gives you the normal vector of this hyperplane. Okay. I'm saying that this vector is on one side of the hyperplane just means that the angle, for example, is acute with the normal vector, whereas the cone makes an angle of more than 90 degrees. So that's what it means to be on the other side. So if you remember Q dot product, if the dot product is positive, the angle between the vectors is acute. And if the dot product is negative, the angle between the vectors is acute. So kind of like the mathematical way of writing this is that there's a vector y where this dot product with the minus the gradient is positive, and a vector y where the dot product with every element of the product is negative. It's not there. That's how forward to be. Sorry about my no. Otherwise, writing this out was forever, but I thought it was useful. So, if you have the flavor of how these arguments work, that's a lot of stuff. Okay, but as you may remember, there's always some freedom when we talk about the normal vector to a hyperplane or to a plane because its length doesn't really matter, right? So if you rescale the vector, that here comes the epsilon. If you take an epsilon, which I'm going to think about it as being super small in a moment, but if you rescale this vector by multiply by epsilon, right, that just like shrinks its length. So it's still, like this rescaled vector is still a normal vector, so still, the same inequalities work, which is kind of like obvious. You just multiply each inequality by epsilon. It is the same, but it's kind of geometrically where you're thinking of doing it and you're rescaling the normal vector by epsilon. Okay. But that's actually going to be a useful trick in the book. Okay. And again, this y can be, it's just like the normal vector to the hyperplane. So it can be anything. There's no restrictions on where it lives. Okay, so y can be, doesn't have to satisfy not an element of the convex set or anything like that. So it's like some vector in Rn that serves as the normal vector to the hyperplane. Okay, and now comes the next step. So now I'm going to take the local mean, the point where the local mean happens, and I'm going to add this epsilon by 1. So I'm going to just add those two vectors together. Okay, so it moves a little bit in the direction of the vector epsilon 1. Okay, so that's going to be absence. My goal, I mean, just to spell out what I want to show, my goal is that I want to show that these x will be in the convex set. Okay. That's what I want to show. So you're trying to do this is. Yeah, I'll get the contradiction. I know, yeah. I'm just trying to work out all the details about what you can get if you're assuming that this does happen. Yeah. Right. But I want to show, eventually I should get something stupid, right? Because it's supposed to be a proof by contradiction. It just takes a while to get. Right? But my idea, right, my goal, again, we already knew that this is already in the convex set. Epsilon y can be anything, so I don't know where it is. But what I'm saying is that if you kind of like, if you define x this way, so kind of like just to make a picture, if this had been like the place of x mean, and then epsilon y, I don't know, it's kind of like the triangle, like the parallelogram law for adding vectors, right? Like this is epsilon y, then this is what I'm calling x. X is the sum of those two vectors. Right, so what I'm saying is that what I'm going to say is that if epsilon is small enough, once epsilon becomes small enough, x is going to be the complex set. And that would give me the contradiction, which is not clear for y, it would, but it will become clear in the complex. Okay, so this is, I want to prove x is in the convex set. How do you prove that? Like again, the condition for being in the convex set was that A transpose times X. This is what it means to be in the convex set, that A transpose times X is less or equal to E. Okay. Or again, like maybe I should have done this like. Yeah, let me rewrite it. I'll shrink this because I don't want to do it this way. So yeah, I'll put it on this side if needed. But so again, what I want to prove, so what I want, again, being the convex set means that AI dot X is equal to BI for every I. Okay. But like this is a system of linear inequality. That's what it means in the convex set. So I'll kind of like prove it in two separate cases. One is when this index I happens to be in the activation set, and the other one where. But first, before I do that, let me just write that down. So this is just the same as showing that. So you want to show that AI dot X mean plus AI, well, dot epsilon Y should be less or equal to BI. Okay, so if I is one of the indices of the activation set, right? If I belongs to the activation set, remember the activation set is where the inequality is achieved. So AI dot X mean would be BI. So if so it's kind of like two cases. Case I belongs to activation set. So if you're in that situation, that means that AI dot X mean is BI. Okay. So the inequality, you have a BI here as well. So what happens with this inequality? Oops. So you have a BI here as well, so the BI is cancelled, right? So you only need to show, right? So to show this inequality, you just have to show that AI dot epsilon y is less or equal to 0. Right, that's what you need to show, which is kind of coming from free from the assumption that we're in this case, you go back. That is essentially what this meant, like, that like the product or less free. Right? So this is coming for free, right? Like that's okay. That's not like that pretending that this impossible case happens guarantees that this. Um, so this is true because of like we are pretending that you can separate things by hypothesis. Oh, and then what is the other case? The other case is when the index is not in the activation set. What does it mean to not be in the activation set? That means that this dot product is strictly less than BI, right? So because it's strictly less, there is a gap between those two values, which I'm calling epsilon I. Okay, so that's going how much, how much they these two numbers different. They're not the equality is not achieved, so there's some gap. Okay. Well, let's again, what is AI dot X? So again, AI dot X is AI dot X mean plus epsilon AI dot Y. Okay. But what is you can use this to solve for AI dot X mean. So AI dot X mean is just BI minus epsilon I plus epsilon AI dot Y. And again, epsilon is a positive quantity. That's when you have to epsilon I is a positive quantity. Okay. So I mean, there's some limit again. But I'll just tell you. Just think about what happens if you again epsilon can be any small. If you're not taking real analysis, you'll get more type of argument. But epsilon was allowed to be any arbitrarily small non-negative quantity, right? So in the limit, and this doesn't depend on epsilon at all, but only dependent on the minimum value for xi. So in the limit as epsilon goes to 0, right? What happens as epsilon goes to 0? This goes away, right? This goes away and you just get pi minus epsilon I, which is a little bit less than that's equal to pi. So that's why if you take epsilon small enough, these will eventually be, this is going to be less or equal to pi. If you ever have done the epsilon delta definitions of limits, like you can kind of play with this a little bit better, but maybe I want to beside the point. We show that at this moment, but here you can see from just that make it more time. But kind of like basically, what you should think about this is like epsilon is going to 0, so this contribution almost it becomes super negligible in the limit, as negligible as we need it to be, and so eventually this will all be underneath, like and that's what we wanted because that tells you that for epsilon small, X satisfies the condition for being in the complex set.
Where do you do that?
AI, AI happens. Use AI. Or something. Well, I mean, it's not, I mean, I'm thinking that, right, like, we're kind of like thinking about what the limit would be as epsilon becomes zero, but you know, like, you never really said it equals to zero, right? Like, that's how this, like, limit argument always work. You're arbitrarily close to zero. But I'm just saying, like, as epsilon gets smaller and smaller, right? Then this dot product matters less and less because you get, getting multiplied by zero, right?
It's epsilon times that dot product.
Right, it's epsilon.
It's like so much smaller than epsilon itself.
Well, so no, so what I'm saying is that, you know,
What if negative epsilon? But then that's base for epsilon, the base is the same small number than.
the thing is like this is epsilon I, which is different from epsilon, right? Yeah. Like no, right, like you know, epsilon I is kind of like the gap between bi. Epsilon I is a gap between bi and ai dot x. Mean, so it's not epsilon. It's different from epsilon. You know, it's like it's a you know a slightly different thing. What the only thing I'm saying is that you know. The only thing I'm saying is that if you do this dot product, you know, in the limit, this or sorry, what was this? It was what? This is just the normal vector to the hyperplane. This doesn't depend, you know, that's provided for you for free because we're assuming by contradiction that this normal vector exists. So this doesn't depend on epsilon. This doesn't depend on epsilon. These are just like the coefficients of the linear inequalities. So this is just like a number, whatever it is. I don't know. I don't care what it is. So this is regardless of what you know this number is. This is always going to be zero in the limit. You see what I mean?
Yeah.
Yeah. So this is called once epsilon is super really close to zero, then this basically is negligible, right? And this is what dominates. But this is a little bit less than vi because epsilon I is a positive quantity. So that's why you can say that this is all doesn't put down. I mean, it takes a while. Yeah. You know, it's a bit somewhat of a sort of point, you know. But you play. I mean, I wasn't not sure like how much to do about the proof, but I felt like it's good to kind of give a flavor of the proof at least once like doing the course, you know, like because especially the KKT conditions are useful, important enough so that you kind of see how many elements come into play. But you know, like you don't have to like worry too much about the proof, like you know, like the picture is what matters. Like that's why I started with the picture. Like what I was trying to say is that you know if you go to the picture, what I was trying to say is that this is what you wanted to show, but this is very hard to show directly. The beauty of Farkas lemma is that you show that the other thing does not happen, and that forces
Not
it.
one or the other.
Yeah, it's like that's the alternative. This is kind of like a special case of something that's called a fractal alternative, but that's like for operators, like in functional analysis. So it's kind of like a that is a lot, like actually many times when you want to show that a partial differential equation or something like that exists, you know, you have a kind of like similar alternatives. So you prove that one does not happen and then that forces the other one to happen and then you have your existence. So it's kind of like the fun thing about this, like this type of results, like you know that just one of the two things can happen. So yeah, like the details themselves of how this happens, I'm just trying to show you a little bit of what's behind the picture, but you know, it's kind of like understanding this picture is like the most important thing, right? Because it's kind of like this interaction going back and forth in the two. But I mean, if you just okay, let's just buy for a moment that this let's buy for a moment that and then this vector x is inside the convex set. Why is that useful? Why is that useful to know that x is in the convex set? Because before the Thanksgiving break, we did prove, if you remember, we did prove that when you have a local mean in a convex set, then the gradient at the evaluated the local mean dot x minus x mean is always greater or equal to 0. We did prove that last time in the direction of the 0. So that comes for free as long as x belongs to the convex set. So that's why we needed x in the convex set. Okay. So this is from like last lecture, like this is from last lecture. We had this inequality. But what is x minus x min? If you just look at the formula, x minus x min was this thing that I'm calling epsilon y. You know, if you look at the definition of x was x min plus epsilon y. Okay. So epsilon is it's a positive number, so you can divide by both sides by 8 and then inequality. So that means that the gradient dot y should be greater or equal to 0. But on the other hand, we also knew that minus the gradient dot y is also greater than 0, right? So you cannot have simultaneously that the gradient and minus the gradient dot y are both greater than 0. That's where the contradiction comes from.
Because it would be an opposite to them.
Yeah, right, exactly. It's in opposite to what that's talking about. But it's kind of like saying that it's acute, you know, the angle is acute minus the vector, and the vector has this an acute angle with the normal one, which cannot happen.
So where do we start with the final statement that's the final division? Where did that final statement?
Oh, this one? Oh, this came for free again, by assuming that you could separate them.
Oh,
Once you pretend that you can separate them, then you know you can choose the normal vector so that these two were at an acute angle. And then, but what I'm saying is that, oh, that's actually happening also with the gradient, you know, but the gradient, right, in this picture is supposed to kind of like be pointed this way. So how can it be, you know, both cannot have that an acute angle with the normal. It's kind of fun. It takes like, you know, it takes some time to absorb the idea, but it's kind of like a cool interplay, you know, just kind of like give you a flavor of how these arguments work. Because again, convexity is an important idea, so it's good to see this implemented in practice. And then, okay, now we can return to this special case, like this silly case, which is much easier than what we were doing. Like, you know, in this, again, like we were trying to kind of like find, we were trying, going back to kind of like our original case, and then I'll put the matrix version, you know, I'm still not in the matrix version, but going back to this, where like you're trying to find the minimum of a function. But the variables have to be non-negative. Every variable is non-negative. So you're working in the first, like in the, you know, in 2D, where is are you trying to find the mean? In 2D, you would be trying to find the mean on the first quadrant, right? If all the variables are non-negative. And in 3D, where are you trying to find the mean? Kind of like in the first octet, you know, like what you would call like the first octet. So when you have more variables, it's kind of like the generalization of the first octet, right? Like you're trying to find the mean in that kind of box or path box. I don't know how to want to describe it. Well, I mean, so you just have to rewrite the way I wrote the constraints. It looks like the variable on the left hand side, right? And you just move, like, you know, just flip the inequality. So that means you're trying to find the mean where minus x is less or equal to the 0 vector with the same. Okay. And another way to write it is that that's the same as saying that minus the identity matrix times the vector x is less or equal to the 0 vector. So this is kind of like our matrix A. In this case, this is our matrix B. And, you know, if you want to rewrite, kind of like looks like an overkill because everything is so simple, but I'm just saying just so that it looks in this format that AX transpose equal. I mean, A transpose X, but like the matrix identity is symmetric, so who cares whether you do the transpose or not. But I still can call it A transpose, so just to be consistent. And the columns of the identity matrix are just like the basic vectors, right? Like the basic ones, I or the canonical basis, IJK, or the generalizations of those. So the KKT conditions what the KKT says is that you can find a vector of Lagrange multiplier. That's the thing, like this vector lambda represents the Lagrange multiplier. There's one for each inequality. So you find a vector of Lagrange multipliers, which each entry being non-negative. That's what means when I write here greater or equal to the zero vector, right? And bigger negative. Where this thing is in between the gradient minus lambda with the zero vector. And the complementary slackness, which is the lambda times xi equals zero, which again is a special case. Before we had it like, no.
Lambda's not, I know.
No, it's just like in the Lagrange multiplier, they're called lambdas, like, but there's not necessarily, I'm not thinking about this as like an eigenvalue of anything, Yeah, I mean, it's kind of, I don't, yeah, it's kind of like maybe an accident of confusion, notation why, right? We call the lambda and think about eigenvalue, but it's not being meant for that way. And again, this is just a special case of like what the KKT said before. So, if these two have to multiply to zero, it just means that either the Lagrange multiplier is one of the Lagrange multipliers here is zero, or the corresponding variable to that inequality. So kind of like one at a time must be like either lambda I zero or xi. So kind of like a more fancy way of writing this is that if you are a point in the mean, if you're at a local mean of the function, so two things must happen. The gradient is greater or equal to zero in the sense that every entry of the gradient is non-negative. That's what I mean by this. Every entry of the gradient must be non-negative, and either this should have been one of the partial derivatives. So either one of the partials, the derivative of the gradient, we put one of the variables be zero, or if that doesn't happen, then it's the corresponding variable xi. So it is similar to, again, in the unconstrained case, in the unconstrained case, we said all the gradient vanishes, right? So we always say this. So in this very simple constraint, you allow for the possibility of the gradient not vanish, like one of the entries of the gradient not being zero, but if one of the entries of the gradient is not zero, then the corresponding value for x, the corresponding coordinate. And how does this relate to the matrix case? So so again, just to go back to the matrix, not for the matrix, the negative factorization of the matrix. What was the setup? You had a matrix A. You had a matrix A where every entry of the matrix was not negative. Okay. And you wanted to factorize it as a product, right? Kind of like a very, similar to kind of the idea of an SPD, right? But where every factor, like we break it as a product of two matrices, each of them having non-negative entries. Right, and the idea is that, if this was n by n, right, this would be n by r plus, and then r plus by n, where r plus is a non-negative, right? Like the minimum number for which you can do this was the non-negative rank of the matrix, which in general is greater or equal, right? Um, in general is greater or equal to the rank of the matrix A. And so, again, kind of like in the same way in which you'd be trying to find, not an exact representation, but kind of like a low rank approximation for the matrix. You can find a low positive, non-negative rank approximation for the matrix. So you would have a function that depends on the matrices A, W, and H, and you want to minimize the distance of the matrix A to the product of the function of those two matrices W, H. Okay. And what I had mentioned, like even in the and it's subject to each matrix being W and H region there. So we had talked about something like similar idea in the regular rank phase. What I can mention in this case is that this is hard to minimize because it's like a very complicated function. So you can kind of like freeze one variable at a time or freeze one matrix at a time and just solve that block optimization problem or to minimize for respect to one matrix. Kind of like as an alternating scheme where you kind of like fix a matrix W0 and then you find that H that minimizes the distance. Then you have that H, then you find the W that minimizes the distance with this new H, and you kind of like do a back and forth. The difference is that here, when you do the back and forth, you're trying to do it in such a way that the matrix always have a negative, and that's kind of like the expert condition. So that's what I'm explaining here. So we're trying to imagine that you fix it as starting, you initialize the algorithm with the matrix W0, which is all non-negative entries, and you're trying to find the matrix H that minimizes the distance, subject also to the condition that all the entries of the matrix H are non-negative. And that is just like a version of KKT. If you think of this function as a function of the entries of H, that is what we just were discussing. So because of KKT, basically what you need is the gradient of this function, if you call this like the function f, the gradient of this function with respect to the matrix H has each of the entries of that gradient has to be non-negative entry-wise. That's why I meant here that each entry of this gradient must be non-negative. And then you have this, which is like the analog of the slack condition, the complementary slackness, which is either, so this HI is kind of like Xi from before. So either the variable is zero or the gradient at that particular variable is zero. So it's kind of like, and that is in practice, it's insane. There are entire books that they discuss like negative matrix factorizations. Like, this one is actually really good. But this is kind of like one of the algorithms for like trying to find an approximation of them. And this has many applications. I mentioned this like about the topics where back document model, like another things. But yeah, like there are many variations of like this idea, but that's kind of like a set of stuff. Okay, and then it kind of it is kind of like roughly what's going behind it. You see, I think it's a useful thing to see because again, like many optimization problems, they have constraints, right? So it's kind of like people to understand like um that works in certain kind of situation. What I'll explain to you on Tuesday is maybe just to and that would be the last topic for the course that I wanted to talk about. So next time on Tuesday. I'm going to talk about the matrix and tensor completion problems.
So again, this matrix completion is related to this Netflix problem. Which was a real problem. Like Netflix literally offered like $1 million to anyone who would improve the algorithm. Like this happened, like, I don't know, what, maybe 10, 15 years ago. I don't remember like the precise date. But when you watch a movie on Netflix, you can, I never ranked them for some reason, but like people like to rank them, right? So like you give 1 to 5 stars. So you can have like a ranking matrix. I don't know if that's kind of like the name that they go by, but you can have like a ranking matrix where here, like maybe you have like one of the indices is for the user, right? And the other index is for each movie, or so like for example, how did this user rank these movies from 1 to 5? So like the entries would be 1 to 5 for like a 5 star, so you can give up to a matrix, right? Yes, not to up to a matrix, up to a movie, right? Like any movie, like, but many users don't like rank the movies at all, right? So this matrix is incomplete by any sense of like the imagination, right? Like you don't have complete access to this matrix because um no, many entries are missing, right? That's kind of like the idea. And also kind of like the point of the recommendation algorithm is that we want to, predict or give a recommendation to someone based on what how other users have ranked, like simply the movies. So like even if you had access to, the entire matrix somehow, like maybe you don't want to use all of it because you want to use part of the matrix as a prediction model for what you should recommend to other users. So kind of like the idea here is to pretend, right? Like you imagine that you have access only to a subset of all the entries of the matrix, which is very realistic because also if you think about the tensor case, the tensor can have exponentially many entries, right? So it is not realistic to think also that you have access to the entire entries of the tensor either. So it's kind of like a useful thing to consider that you don't know the entire object completely, right? So you assume that you have access to just a subset of all the entries of the matrix. And then you want to find the best way, in some way, to fill in the remaining entries. Like what should be the best way to fill in the remaining? Okay. So you're trying to find. So the goal is to find. At what time? Okay. At what time did we start? 2 p.m. to 3:20. All right. I'm still we. Okay, good. I was like, did I? I was already going over time. So I can feel the motivation. So you want to find a matrix. I'll write it a com for completion. It's like my attempt to complete the matrix, right? Like I'm pretending that I don't know all of it. Well, I'm not being too fancy in how I'm writing it, but what I'm trying to say is that the matrix agrees with the original matrix at those values that right? Those like indices that at the known entries. Okay, and then okay, so that definitely seems like a very natural condition. But if you just say that, obviously there are infinitely many ways to complete the matrix, right? Like you could just put zeros everywhere else. You could put just ones everywhere else. You have to find an extra condition to make the problem interesting. So, why don't we try to find the completion which the possible lowest rank, the lowest rank possible? Because again, the lower the rank, the more simple the matrix is, right? So it does make sense. So the keyword if the matrix has fewer ranks, there are kind of like fewer causes, it's kind of like, you can think of like, having a matrix of low rank as meaning kind of like there like a couple of factors that explain all the user's preferences. So it's kind of like the least amount of independent causes that predict how someone ranks them up. It's kind of like an outcome tracer principle. If you have heard about it before, which often phrase where says that among all the explanations, you kind of like choose the most simple one. So in a sense, the lower the rank, the more simple the matrix is. So if you have to choose between one that had rank 20 versus one that had rank 2,000, I really think that the matrix with rank 2,000. So the idea is that here you try to find the matrix, the completion that agrees with the given one at those known values, but also has the least possible rank, but also where the rank, but with the smallest rank. So basically what you're trying to do is like, you're trying to solve a problem like this. You're trying to solve like a, you know. So you're trying to minimize something, you're trying to minimize the rank function, right, of the completion matrix subject to a constraint. A constraint is the agreement with the entries that are known. So there's like a constraint, it's like a, subject to so this is what I'll tell you about the next time. This is kind of like theoretically the problem you would like to tackle. It's just that the rank function behaves terribly. Like the rank function, first is discrete, so it jumps, right? It jumps all over the place, it's not convex. So you convexify it. So you do a convex relaxation. So like that's again also a very useful idea from optimization work. This is what happens in integer programming where you're trying to find solutions that are integers, but sometimes you relax the problem by, for example, allowing if in the case of Boolean variables, say where like the values could be only 0, 1, you relax the problem by allowing the value to be any number between 0 and 1, for example. That kind of like makes it easy to solve because then you kind of give more like needs from something to another. So there's a kind of like a similar idea here where like I'll tell you about this next time, but the rank function is like a terrible function to work with because it jumps, it's not convex. So you find the convex function that's closest to the rank, and that's called the spectral number of a matrix, which is the sum of the singular values. So I'll explain that next time. It's kind of like very cool. So instead, you try to minimize the sum of the singular values of the matrix, and that can be done as a convex optimization. And then there's like a similar idea for tensors, because the tensors don't have singular values, so you have to do a fixed tensor, but I also told you how to do it. So it's not like a very fun thing to discuss this. And then it's like a way to end the course because it's still connected to convex optimization, which is like a, again, like it's very important. Yeah. And then that's topic. Good.